computer write a symphony? I know, it sounds a little like science fiction, doesn't it? But what if music itself is kind of like a language, or maybe even a game? It turns out, if you can figure out the rules, you can actually teach a machine to play. And that's exactly what we're diving into today, the amazing world of algorithmic composition, where code and creativity collide. All right, so here's what we've got on deck. We'll start with music by the numbers, looking at a pretty surprising historical example. Then we'll get into a couple of really big ideas, music as a kind of grammar and music as geometry. After that, we'll check out some modern tools, and we'll wrap it all up with a big question. Where does the human composer fit into all of this?
Okay, first up, music by the numbers. We're going to start by rewinding the clock way before computers to show you that this idea of making music from a set of rules, well, it's not new at all.
So let's kick things off with a big question. We tend to think of art as this deeply human, intuitive thing, right? A flash of inspiration. But what if you could create it with a pair of dice? No joke. We're talking about Wolfgang Amadeus Mozart. He actually created something called a musical dice game. The idea was pretty simple. You roll the dice, and the numbers tell you which pre-written musical snippets to string together. And here's the magic part. No matter what you rolled, it always came out as a coherent, perfectly listenable waltz. It's an absolutely incredible early example of rule-based or generative music. And what Mozart was doing back then? Well, today we have a name for it: algorithmic composition. At its heart, it's just the process of using a formal set of rules, an algorithm, to create music. Think of it like a recipe. You write down all the steps, and then someone, or something, like a computer, can follow that recipe to cook up a brand new piece of music. Okay, on to our next section, a grammar for music. This is where we get into the theories of Heinrich Schenker. Let's shift gears for a second. Instead of thinking about music as just a string of notes, what if it had a deep structure, a grammar, just like a language? This is where a theorist named Heinrich Schenker comes into the picture. Long before anyone was thinking about computers making music, he came up with a way to analyze it that looks a lot like what we now call a generative grammar. He was essentially creating a rulebook for how to speak the language of classical tonal music. Now, the absolute core of Schenker's idea is this concept called the Ursatz, which basically means fundamental structure. The best way to think about it is like the steel frame of a skyscraper. On the outside, you see all this glass and complex detail, but underneath, it all hangs on a very simple, very strong skeleton. Schenker believed that every complex piece of music had one of these simple skeletons at its core. And this is how it works. It's a top-down process. You start with that simple skeleton, the Ursatz. Then you start adding layers of complexity through a process he called transformation, or Verwandlung. You just keep elaborating, adding more and more detail until you get to the finished piece. It's this beautiful hierarchy, starting from a single, simple idea and blossoming into a full-blown masterpiece.
So you might be wondering, okay, that's a neat theory, but how do you turn it into an algorithm? Well, people did exactly that. A system called Choral, for example, used this exact hierarchical idea to harmonize melodies. Thinkers like Lardall and Jackendorf formalized the whole thing into a generative theory of tonal music. And get this, some of the earliest algorithms literally mimicked this process. They generated the baseline first, the foundation, and then build the rest of the harmony on top, just like Schenker's model suggests.
All right, next section, the geometry of harmony, where we'll look at the theories of Hugo Riemann. So get ready to shift your thinking completely. We just talked about music as a top-down tree structure. But what if it's not that at all? What if it's more like a map, a geometric space that you can move around in? And this is the key difference. Schenker's approach is hierarchical. It's top-down. You start with one core idea and build everything out from there. Riemann's approach is totally different. It's geometric and relational. It's not about where you start. It's about the network of connections between all the chords. It's about the moves you can make from one chord to the next. And this geometric map has a name, the Tonnetz, which literally means tone network. It's a grid that beautifully lays out all the relationships between notes and chords. The analogy of a chessboard is perfect here. Every spot on the board is a chord, and there are specific logical moves you can make to get from one to another. So what are the moves on this chessboard? Well, what's called Neo-Riemannian theory boils it down to three fundamental transformations: P, L, and R. Each one is a super simple, really efficient move.
You just change one note in a chord by a tiny step, and boom, you're at a new, closely related chord. It's an incredibly elegant system for moving through harmonic space. And this isn't just some abstract idea for analyzing old music. Composers have actually used this as a blueprint for creating new music. Paul Glass, for example, wrote a whole piece where the entire structure is built using only these P, L, and R moves. And Giovanni Albini used the same system to create a piece that walks through every possible chord in a specific path, totally throwing out the old rules of harmony. Okay, so we've got grammar, we've got geometry. What else is out there? Let's move on to our next section, modern algorithmic tools. So far, the rules we've talked about have been pretty, well, strict. If this, then that. But there's another way to think about it. What if creating the next note in a melody isn't about following a rule, but is just a matter of probability? This is what's known as a Markov chain, and it's a really cool statistical model. Here's how it works. You can feed a computer a ton of music by, let's say, Bach. The computer doesn't try to understand the grammar. It just calculates probabilities. It learns, okay, after a C note, there's a 40% chance the next note is a G, a 20% chance it's an E, and so on. Then, to create new music, the algorithm just starts on a note and basically rolls a weighted die to decide where to go next. The result is new music that sounds a lot like Bach because it follows the same statistical patterns. And of course, it gets even wilder from there. Some people are using super advanced math. We're talking stuff like topos theory for mathematicians like Guerino Mazzola to create these incredibly deep formal models of musical logic. It just goes to show how profound the link between music and pure mathematics really is. Okay, last section, the ghost in the machine, the composer's new partner. And this brings us to the big question, right? With all this powerful technology, where does the human composer fit in? Are we just trying to build a robot that writes music for us? Well, this quote from a pioneer in the field, David Cope, really flips the script. He's talking about his program, and he says that when it starts creating things that are new, that go beyond just imitating a style, it's not just a tool anymore. It becomes an equal partner. It becomes a collaborator. And that right there is the key takeaway. The goal isn't to replace the artist. It's to create a powerful new collaborator. It's about building a tool that can explore the infinite universe of musical possibilities and bring back ideas that maybe a human, on their own, would never have even discovered. And that leaves us with one final, pretty mind-bending question to think about. If an algorithm can be a creative partner, what does that make the composer? Their role changes, right? Maybe they become more of a director, a guide, a curator of ideas. It's a whole new way of thinking about what it means to create art.